Jai Hind to all. My name is Aarti Chaudhary. I'm assistant professor in AKGEC College, IT department. So in today's lecture, we will go for our consensus protocol. What is consensus? Why it is used in blockchain? And what are the uses which we use in a blockchain scenario also? Why we need it? Because as we know that blockchain is a decentralized and distributed architecture. How can we achieve the properties of consensus in our blockchain environments? So all these are the points to be discussed in our subsequent PPTs. Are define what is consensus, what is distributed consensus, what is message passing through we can use in a consensus, why we used a consensus in an open system, because we know that the existing open system, that is Bitcoin. In the Bitcoin also we are having a thing that we don't know about the person who is coming into a network and going outside the network, because it's not a closed network. So in how can we achieve the consensus into a Bitcoin also? What are the ways to use it? How can we achieve it by using our proof of work, POW? And what are the uses by using it, with a live example of it, by having a hash cache. Okay, all these are keywords which we use it. First, what is, why there is a consensus, why we need a consensus? As we know that we are using in a blockchain, or in a today's scenario, we are using a distributed or decentralized architecture, in which we are not rely on the single source. We are having a distributed architecture, where we are having some points of network here, some other points here, and others point here. So we have to depend upon the whole of the network, not the centralized. So because we are having an advantage of fault tolerance there, so we are using in a blockchain also, we are using a reliability and the fault tolerance that we are using here in a distribution. Because what we have to do is to ensure the correct, because we know that in this scenario, any node which goes faulty or having a wrong information, malicious information, that information has to not to be propagated to other person. That makes to be sure to the correct operation in the presence of faulty individual. We are having a faulty, for example, if any node crashes down, so how can it will behave like it will not giving a correct answer, and at that moment also we will give a correct result to it. For example, a real one scenario of this is, example is committing our transactions in a database. For example, in daily basis in banking systems, we are having millions of transactions which will happen, any credit, any debit of the data, any money related. So what we have to do is, if we are having a distributed architecture which is bank is following, they are having a servers here in Bangalore also, here there in Pune also, so see, they are having a distributed architecture. So if any server will go down or having a fault, as having a crash, so that the transaction has to be committed up to where the data has to be sure. If other than for example, we are having T1, T2, T3, T4 transaction, if all these transactions are up to this point is committed and this point is, so we have to iter a rollback. In the database there is a concept of rollback also, up to where we have committed, and then after we have to roll back also. So that the thing we have to be there into be the consensus protocol what we are using in blockchain. Second example is state machine replication. As we know that we are using a distributed architecture, and what we are having is that architecture have a state machine. So every server have a state machine which is having a group of states that is committed to them. So they are communicating with the help of these state machines, and these state machine has to be communicating between a servers, and they give a correct information, how that, for that we can take a information, we can take a input from that information state machine machine information, and then after we will get a result according to that. Next is distributed cloud synchronization. As we knew that which clock is working and which clock is not, we have to be synchronized according to a clock. So all these things has to be a scenario. So any thing which we are using in decentralized also or distributed also, so we are having a faulty nodes also. So we have to, in that scenario, what we have to make it sure that we will result into a correct result accordingly. So this is a problem why the consensus is difficult in certain scenarios. It's an example. It's a example of military also. These are journal 1, for example journal 2, journal 3 and journal 4 we are having a war situation. For example, we are having a war situation, and journal we are giving a that we have to attack them or retreat them. They are having a message passing. If they are having a distributed network, so we are having a message passing that journal G1 will say to this is G2 will say to this attack. So they will say sending to the neighboring node that we have to attack them. If G3 is also sending to a G2 or G4 that you have to attack. The same information attack to both of them because they are the neighboring nodes. And if the G2 they are having saying that we have to attack, and G3 also they are saying it. But at the case of G1, the journal G1 is saying it is a malicious node that they are saying that to one person G2 they are saying the retreat, and to other journal they are saying that it is a attack. So they at the two situation they are saying that you have to retreat also and attack also. The message passing, this node becomes a problem and it will not give a correct result to us. So this creates a problem for us. The procedure to reach a common agreement, we have a common agreement in a scenario which we are having a distributed also and decentralized multi-agent platform, because we are dealing not with a centralized one. As we know that the blockchain we are having a distributed decentralized manner. So what we have to do is we have to make a common agreement, and the agreement has to be positive and has to be correct in nature. So that was to be there. So we are using a technique of message passing here, and in which one of the journal will behave as a marvelously. It is not behaving that at the one person you are at one instant you are saying retreat, and other person journal you are saying that you have to be attacked. So this is creating a problem for us. So that scenario arises into a consensus protocol which will not give us a correct result accordingly. So this is what we are having a distributed consensus. If there is no failure, if we are having a distributed environment and we are having that there is no failure, no crash, nothing, so it is easy to travel to reach our consensus. We will get a positively a result, and that result has to be correct also. Like for example, if we are having a first, second, third and fourth nodes, and it is having a message passing techniques, where the message passing is we have broadcasting the personal information. For example, I am having a party and we are having 4 friends, and 4 friends what we have to order burger, french fries and sandwich and coke and any ice cream. So they have voted just which is a maximum voting that is get ordered. So in this example also we are having a maximum value choice, maximum value of all the values. So how can we say it? To 10 we will get a value of 40 also, neighboring node. Broadcasting is 30 also, and this 20 also. On 40 also they will get a request of which is a neighboring 10, 30 and 20. Here what we are getting is 40, 20 and 30. At here we will get 10, 40 and 30, and here what we are getting is 10, 20 and 40. All is given because there is a no failure condition. We are thinking that this is a scenario of no failure here. So in that scenario we are getting a true information, that is from the neighboring node we are getting, and then after we will see a choice function, and choice function will see that okay, we are getting a request of 10, 20, 30 and 40. Which one is maximum one? That maximum is 40, and that is we will see that the 40 is a maximum function. We will get a maximum value out of it. That is using the message passing. If there is a no failure, I'm just underlining it, that is there is a no failure. But in this but in a real time scenario, the no failure condition will not happen. It will happen, definitely it will happen. So in the distributed condition, there was various types of faults which we are seeing is crash fault, in which a node get drowned and unavailable in the middle of communication, that when we are having a communication and this node gets down, it will communicating this and this, but not like this, because this goes down and it will not sending any information, sending any information, no false information, any not true information. We were okay with it. That is called a fault, for crash fault. Next is network and partitioning. In network and partitioning, for example, we are having a network like this, and this is this connected with this, connected with this and this. If for example this is a node connecting with this, and we are having a fault which makes that is a fault not in a net, it will occur in a network, but the network link get fails, this link get fails, then there is a partition, P1 partition, because this nodes belongs here, and P2 partition where this nodes become this, that the network is partitioned into two, that is partition 1 and partition 2. So there is a fault tolerance. There is a Byzantine fault when the node becomes giving a wrong information. It's not getting down, it's not partitioning, but this is a one of the worst thing when you are giving a wrong information. We don't know that who is a culprit and giving a wrong information. So we have to make that sure that we will identify that the Byzantine faults, which is here in this example also. This journal is giving a wrong information to the journal 2 and journal 4, but that you have to attack also, reiterate also. So this person have to create a problem in our consensus, giving a right result. So okay, so what are the properties which we use in a distributed consensus? That is, first one is termination. Every correct individual decides some value at the end of consensus protocol. So when we are applying any consensus protocol, we will have a surety that every correct individual, every correct problem will arise at the consensus protocol, will give a result which is correct in nature. Next is validity. What we are having a validity, if all the individual propose the same value. If in the previous example 10, 20, 30, 40, all the individual are having some common values, which is this, then all the correct individual decide on that value. If majority of person is saying that all the saying that this value is correct, so then we will have decide on that value. That is validity according to it. Integrity is that every correct individual decide at most one value. Every correct individual will have at most one value, more than one value also, but at most one value, and the deciding value must be proposed by some individual. So because you are the middle person of that architecture for the consensus protocol, you have to arise a correct result. So you have to make sure that the individual have at most one value, and decide on that you will propose a correct value by by some of an individual. Next one is agreement. Every current individual must agree with the same value. So you have to make sure all these 4 parameters has to be satisfy when you are using in our distributed consensus. We are using it into a blockchain. So we are having two scenarios of the message passing, which we are opening with us, that is synchronous and asynchronous. In synchronous, how much time we have to wait? So this is a fixed amount of time, this much second we have to wait for message to circulate, because we are using a message passing technique. So we are having a message that is received by a predefined time interval. So we need that according to that time we will get our answer according to that. So strong guarantee on a message passing delay, because we are having a predefined time interval. So at that predefined time interval we will definitely get a message from the subsequent neighboring nodes, which is used in a distributed consensus protocols. So next is asynchronous. There is no upper bound of it. We are not having an upper bound of the message passing. So also no time constraint. So delay, how much time we have to do. So that scenario is when we are having a distributed consensus protocol, which is actively give a result in a synchronous systems, but we are not give a correct solution, correct result in our asynchronous systems, because that is there is a no upper bound of the time which we are having into it. So that is a problem, that is an open problem which we are having in our asynchronous one. Next, this is asynchronous consensus, in which we are having a problem which is identified in 2001, that is impossibility result. That is proof of impossibility, that is done by a Fisher, Lynch and Peterson, in which LPF 85. In this they are saying a purely asynchronous distributed system. If there is no time constraint, no upper bound. In a distributed system, the consensus protocol is impossible. We are saying that is impossible, which is having a deterministic solution, which we will get a result that is deterministic in nature, that is impossible if we are having a single fault, you can say it, single crash fault. If we are having a system in which single fault is also there, single crash fault also there, we are not getting a deterministic solution in our asynchronous distributed system. This is a research which is published and awarded in 2001. We will get a randomized algorithm of it, but we are not getting a deterministic solution of it. Okay, so we are having a asynchronous distributed system which is impossible in that case. Okay, so we are having a asynchronous continuous consensus protocols which we are having in our hand, but not the asynchronous. So what is the correctness of distributed consensus protocol? First one is that is safety and liveliness. For safety is correct individual must not agree on incorrect version. So what we are having into a distributed or decentralized architecture, we will does not agree on incorrect information. If we are not having the majority will not go to what we are having is incorrect result. We have to give a correct result in a distributed consideration, that is called safety. And this is liveliness. Every correct value must have been accepted eventually. So every good thing will happen eventually. So we are not having a security that face safety is that nothing bad can happen. We will not give a wrong result to you. Liveliness and something that is good will eventually happen accordingly. So this two things we have to be ensured in a distributed computing distributed consensus protocol. So we are having a consensus protocol in an open system. This is a problem for us when we are having a consensus protocol in a Bitcoin. We will see this is what is the problems what will arise when we consensus. We are having two environment, two systems, synchronous and synchronous also. We will arise a problem on asynchronous because we are not having a upper bound of it. If we synchronous, we will get a result, deterministic result according to it. But when we apply the consensus into a open system also, that is having in a Bitcoins, we don't know each other. In a Bitcoin environment, that is a permissionless environment. Sorry, permissionless environment in which what we are having is we don't know about the identity of the person who is into a Bitcoin, because we are having a in and out. They are giving a hash code, and according to that we will attach to a blocks of chains that is there in the blockchain. So what in this thing, when we are having an open system, we have a closed system, we have an identity of persons, but in an open system we are not having an identity. So in the shared memory, it's not suitable for the internet grid computing. Where do we put the shared memory, because we are not having a shared system into it. So in the Bitcoin also we are having is anyone can join the network at any time. So we don't know about the identity, who is a faulty person, who is making a fault, who is crashing, who is saying. So all these things are not maintained into an open system. So this is a challenge for us to for the consensus in an open system. So we are having to ensure that how can we move to a open system consensus protocol, what we are seeing in our case. So why do we require consensus? Because when we are having a peer-to-peer, if Alice, example, Alice is broadcasting a transaction to peer-to-peer network, that is broadcasting they are doing. So it is doing to neighboring nodes, then neighboring nodes is doing for other neighboring nodes, neighboring nodes is doing for other neighboring nodes. So in this is a broadcasting, that is flooding of message. All the nodes in a network need to agree the correctness of this transaction. So you have to make a transaction that is broadcasting, that is flooding, and that flooding has to be so that we have to be, Alice is saying to the neighboring nodes that this Bobby has paid this to me by using a signature of the Alice and all that formalities with the hash function. Then all that message is flooded into a network, because it is our open network. We don't know about the nodes which are connected for us. We don't know the identity of the nodes which is used into a Bitcoin open network. What we are saying, because they are we don't know about, because this is called a permissionless network. We don't know and don't need any permission to enter into it. We just have a person and then we will enter to it. Okay. Next we are having consensus into a Bitcoin network. Every node have a block of a transaction. So in our blockchain we are having a nodes, and we are having a transaction T1, T2, T3 and up to transaction. We will create, if these transactions are committed, we will add to our blocks, and then after we will create a block of chain. This is a blockchain we are having. The every node have a block of transaction that already reached in a consensus, and the block of a committed transactions. So that block has to be committed the transaction. The node has to be making that when what we have a problem is the uncommitted transaction, outstanding commission that is not validated. This is a scenario when we are creating a blockchain. Then I will show you to you that if we are having a scenario, this block, that timestamp, noise, that is transaction route, previous has, because they are connected to a interlink, like a linked list also. So they are interlinked by a hash value. All these hash values. So all these hash values will be having a transaction. So these, if it's the transaction is committed and added to a block, then that block has to be committed. This block is to be added to a chain, that is blocks of chain that we are having. So this is transaction. What we have to is, it's a bunch of transaction which is have to be added to a block and become a blockchain. So this is a problem for us. So what we'll say, we will not have per transaction conjunction, that is inefficient. We will not have transactions inefficiently. With a per transaction we will commit it, per transaction we will commit it. So that has to be a block based transaction. In this block based transaction we will have a total 5-6 transaction and then commit it, and then after we will add to a block to it, and then after we will that a block to be added. This is a block of chains. Apply consensus over the entire block, and then after we will get a result of a blockchain here. Okay, then what is that? When we are having a blockchain objective, Bitcoin consensus objective, in which we are having a blocks of chain, and for example we are a miner 1, -2 and -3 if we are having. We know that transaction once 1 to 14 is committed, we will go for a 15, 16, 17, 18, 19. All these transactions has to be committed because the transaction number we are giving in an increasing order. So we are having 3 minus what we have. So which transaction has to be committed and which will be added to a blockchain is our task for us, because we are having 3 miners, we are having a resources, and that resources has to be provided to them. So what are the parameters? How can we say that the block which is attached, which we are having, is to be committed and added to this block or this block? We will see that which block will be the next for us. So that is our first one. So what are the possible solution? It is broadcast the information and apply a choice choice function. Traditionally what they will broadcast is I have this transaction, number of transaction, this number of transaction, this number of transaction, that is message passing. And if they are not giving a correct information, who is validating us? But this, so that traditional distributed conversion algorithm will not work here. So we will say that proof of work will be help for it. So we will have our observations. In this observation, what we are having is any valid block, that is any block, this block, this block, or this block, any block which is, this is optional for us. So any valid block, a block with a valid transaction can be accepted even if it proposed by only one miner. So any valid, how can we do that? Any validity of any block, how can you do that? So we having a problem of it that is to be that has to be increased into it. So these are the observation 1. Observation 2 is broadcasting it and making a next set of it. So we are having a solution of proof first. Proven first, that is who will prove first, we will accept it, and then after we will add it. So this is a thing. So I have a solution, who will prove first, it will broadcast to it this and this, and that I have a solution, this I have a solution, and this is get added to it. Okay. So but we will see that if it's doing first, so it will add it to a block, then after everyone will see that broadcasting of the block, because that is the next block of the blockchain. So it will say that 18 is committed, 19 is committed, but 17 is not committed. So they are including 17 into it. 18 is committed, 19 is committed, 20, 21, 22, 23, 17, 20, 21, 22, 23. So others miners will include into that block and then after mine it. So that is the problem, that how can we, if the person have mined the block, so how can we authenticate that is a proof of work. So the measured measure to detect services abused by someone, that I have done some work, so requester will do it and then after the authenticator will prove it. So like for example, if we are having a example, the authentic mail and the junk mail, how can we differ it, that this is a junk mail and this is a authentic mail? So we will see by using a proof of work. So in this we are having that the asymmetric property. In this the work must be moderately hard but feasible for a requester. It will do it, but for the provider it is easy to authenticate. Okay, you have done this, I will authenticate it. So it will the service requester, it will discourage them to do the work, to do the forgery, but the provider will check the validity. So it's easy for them, for the provider, but requester ke liye it will discouraging work for them. So it will having a hash cache by having a puzzle friendliness property, in which we are having x and y, and if we have to calculate k. For our requester it is difficult, but it's feasible. It's not it is feasible, it's not infeasible, but it's feasible to calculate k. But if when we get k, so it is easy for which it is easy for the provider to validate it. Okay, so when it is for a requester, it is a feasible, but it is a difficult task, but for the provider it is a quite problematic, it is easy for them. So we are having a hash cache POVW, in which we are having a use into a junk mail and validating mail, valid mail or junk mail. So they are having a you have to work, a spanner have to work some things bigger, and then after validator have to make it a hash code, is it authentic or not, by using it. So we are having a spanner here which have a difficult work, and the authenticator you have to be less work for, receiver work for. For example, the Hashcash POV, in which we are having a version here, Hashcash we are having, in which date we are having valid email ID. Then after we will say that we have to add 20 bit of prefix, 10 bit of prefix. So that is my choice, because I am the sender who is sending. That is a junk mail or this. If I am a spanner, so I have to recalculate it. So we are having a date, email ID, resources, optional, extension, how much bits we are having a randomized, and then we are having a counter of it. This is included into every hash, every email header, that is included into your email header. So at the receiver side, what we have, that date has to within the 2 days, email ID valid hogi, and then after randomized string, that has to be used repetitively during the mention. So that randomize has not been repetitively, because if we are having a replay attack, they are having a repetitively same hash code. So we will say that this is a replay attack. So but when you have a randomized string, that is has to be certain, not repetitively on the previous one. So we will compute a 160 hash code, and then after generated, that is a valid or non-valid. If it's not valid, if the first 20 bits are not zeros, they will say that it's not valid. If it's first 20 bits are zeros, we will have saying a valid. So for that, what are the average senders hash code we will generate? 2 raised to power 20, and if it's having a beginning, so if we are having a 200, this much possibility we are having. So that at the receiver side, it will take a 2 microseconds to validate it, but at the sender side, to generate it, it will take a 2 raised to power 140 possible hash to make that criteria. So the working for the spanner has to be more, because they are the generator of it, but for the validator at the receipt side, they are easy to validate it. We are making that easy for us to differentiate between junk mail and the valid mail. Okay, so this is the how we can use the Bitcoin proof of work here, and we will discourage the miners who are validating, who are making that thing that miner will need to give a proof to when they are doing some work or proposing any block to a blockchain, and the attacker will discourage to propose a new block or changes into existing block, because you can't change a hash, because they are connected with the hash, previous hash. You have to continuously change in every hash, that is generics block, and then after you will make it. That is very much, that's why we are having a 51% attack. You have to attack for 51%. Okay. So this is a solution for having a open system consensus protocol. So that's what the difficulty which we are facing in this, and we are having a block hash also, previous block has a Merkle root tree also, noise also. So that's why we will calculate the noise, and the person will validating it. So this is the end our PPT, in which we are having consensus protocols, consensus in distributed system, how we are validating it, what are the proof of work we will do it, how can we hash code with the help of junk mails and validating mails. This ends our problem, that is consensus protocols here. Thank you.